What's up, heathens? How y'all doing? Today we're going to take another look at one of my Flaturday night fights. It's the one with Chris Berry. He's a flat earther and he's going to try to explain a couple things. One is relative density and how that disputes gravity, and another is how the sun operates in the sky on the flat earth and why we seem to see the sun set and why the sun rises. He's going to do a very poor job of explaining himself, and he's going to contradict himself in the last video we posted here. So if you haven't seen that one, there will be a card up above to go and view it. If you have, then please just sit back and enjoy this part of the discussion.
GE and I grant you that you win on the photographic evidence there. It's just for sake of talking, we say that. Is that your main evidence for why the Earth is not a globe, or do you have something else that you would point to? Like, how do you explain gravity? Do you believe in gravity?
No.
Okay, what's your explanation for that?
So the best explanation that I've seen now is the relative density argument, which, I mean, I'm sure you're familiar with, but for the audience's sake, it's basically saying that the relative density of one object determines where that object fits in the relative scheme of, you know, their environment. So if you drop a pin, the pin falls because it's heavier, it's more dense, if you will, than the air around it. Whereas if you let go of a helium balloon, the helium balloon rises because it's less dense. So it's kind of oversimplified, but that's really the gist of the concept.
Okay. Now, I get that you said earlier that you're no mathematician or anything like that, but would you happen to know, like, how buoyancy is calculated or the buoyant force or anything like that?
Sure. Yes.
I'm sorry, I didn't get that.
Yes.
Oh, okay. Could you tell me what the formula for buoyancy is?
Well, I know where you're getting at, and what you're getting at is that the little g acceleration is in the formula. The problem, though, is little g, you can make things move due to buoyancy or density without changing little g, right? So you've seen the egg and the water test, where if you put an egg in normal, call it tap water, salt-free tap water, the egg will fall because it's more dense than the water. And then if you change the density of the water by adding salt and mixing it in, it increases the density, and therefore it makes the water heavier than the egg, so the egg rises. So no matter if you use the density formula or the buoyancy formula, little g isn't changing. The density and the mass of the water is changing to cause the motion.
Okay, do you know how buoyancy is actually calculated in order to know whether or not the particular object will sink or fall?
Why don't you just tell me so we're on the same page?
What?
Just tell him so that you're on the same page.
Oh, okay. Well, basically, as far as buoyancy goes, when something sinks, that means that the density displaced by that object, or not density, but the amount of water displaced by that object, I'm trying to remember when I researched this. Basically, it's a summation of the forces that are acting on the egg, right? So when the summation of the forces that are acting on that egg are in one particular direction, it will sink. And when the summation of the forces happening on the egg are in a different direction, it floats, basically. And so the forces that are acting on that's why gravity is factored into it, because gravity is pulling down on the object. And so the amount of force that is pushing up on that object, if that doesn't equal, or if it's not equal to or greater than the force of gravity acting on that object, then it will float. If the force of gravity acting on that object is greater than the force that the liquid is exerting on that particular object, it will sink. So you have to take into account some force that is causing it to go down. And can we agree to the basic laws of motion? Like, can we start off on that foot? Like, do you agree that an object that is at rest stays at rest?
Well, let me ask something here. I think this is a good question. Since you said this a second ago, you said that the density formula gets the same results as the buoyancy formula. Can you cite the density formula?
No, I didn't say that's exactly like that. What I said was whether you use density formula or buoyancy formula, when you're changing the mass, the density, which is basically changing the mass of the water in that egg example. So for example, if you use density formula, density equals mass over volume. So to get the egg to move up, you're changing mass in that formula, if you will, in that test. So by changing mass, you're causing a movement. You're causing the motion by changing the mass. You're not changing gravity.
Well, right. You're not changing gravity. You are changing the mass of the liquid. But I mean, that's all part of the buoyant formula, and the buoyant formula requires some force pulling down on the object to give it weight.
Let's go simple right here. Go simple right here. If you look up in the sky and you see things like objects like the moon and other planets, what do you think those are real?
Yes.
Okay, so if the moon is real and it's a sphere, and all the planets are real and they're spheres, why would this planet be any different?
Well, I mean, obviously, I can't answer that question, so I'm speculating purely based on opinion. It would have to be the uniqueness and the specialty of the Earth in terms of some type of creator. I've said this before, and I'll say it again. I don't care what side you're on. If you believe the Earth is flat, there's no way that happened by chance, right? It had to have been created by something or someone or some entity, whether that's aliens or a godlike creator.
So here's my issue there, though. You're willing to go out on a limb and say that even as far as aliens created a flat planet for us to inhabit. Yet when we have things like gravity, which explain that objects that have the mass that these planets do are going to pull themselves into a sphere. The mathematics are there. It can be demonstrated to be such. That explains it. Very neat, very tidy. We don't have to go into aliens maybe did the flat Earth or a god.
How do you demonstrate gravity forming something into a round sphere?
You look around. Look at the moon. Look at Jupiter. Look at Mercury. All of these planets.
Well, that's you're putting your answer into the question. You're saying, how do we know that X is real? Well, look over there. That's X, so we know it's real, right? Or we know that is the cause. We don't know what the cause is. It's a begging the question fallacy.
There's a formula that you can do.
We don't know without tests and experimentation.
There is. There's a mathematical formula that demonstrates that things that they're with that sort of mass will pull themselves into a sphere. But my ultimate point, whether you want to call it a begging the question fallacy, that's fine. I'll grant you that. Why is this planet flat? And without having to move to aliens or God, why would this planet be any different? You're taking that on faith. You know that, right? I mean, it's not something that
no.
tangibly. Yeah, that is faith. That's absolutely faith.
That this planet is flat is faith?
Yeah, because you just said that it would have to be made by a creator. You can't demonstrate that creator, so therefore you're believing that on faith.
No, that's to the question of why would this place be flat and everything else be round, which, by the way, that's an assumption in and of itself. We don't know that they're round, spherical. They're round, but a plate's round and it's flat.
So these could be just angled at such that we're seeing it flat when we look at it.
Yes, or it could be I don't know what you call a sphere cut in half. A sphere cut in half. I mean, who knows? Like, we don't know for sure what the actual shape of those objects are, other than this circular, basically what your logo is, a circular disc.
Okay, so if that were the case, why is it that we can see different texture on those particular objects? Like, as well as in reality they rotate on their axis. How do you explain that? Like, you might be able to get away with this whole plate theory with the moon because it's tidally locked with the Earth, but I mean, other planets rotate. Like Mars, it rotates, and you can actually get telescopes here, powerful enough, just like any regular consumer can go and get a powerful telescope and see Mars. And I mean, you can see it, and you can take pictures of it or even video of it, and you can see it rotating. How do you explain that?
See the topography of it.
What?
I mean, honestly, I don't even want to go there. I just don't have the knowledge. about the stars and planets. I honestly haven't done a lot of research into that because I like to keep my focus onto the Earth and the ground and the sea, the water.
Okay.
It just
Well,
just
okay,
looking
but
at the
I mean,
sky.
it's a bit of a hypocritical stance to take, don't you think? Because you know enough to know that they're not spheres, or at least know enough to doubt whether or not they are spheres, but you don't know enough to offer an explanation for that.
Yeah, if let's move to planetary bodies that affect this Earth, then that I think you should know of because they affect our everyday life. The sun and the moon. What's your view on them?
That well, it's a general broad question, but basically, I believe that what you might call the generic flat Earth model is that something like that is happening, where the sun and moon are smaller and closer than we've been led to believe, and that they rotate around the, call it, flat plane of Earth.
So okay, so in Dubai, there's the Burj Khalifa, tallest building in the world. You're able to watch the sunset on the bottom floor, and then take an elevator up and watch the sunset again on the top floor. How does that work on a flat Earth?
Well, I mean, there's a couple ways. By raising altitude on a flat Earth, you're changing the angle at which you're looking at something. And that angle change can allow you to see more further on. It's the same reason when in all these videos that you see of like planes and high altitude balloons, that as those balloons or planes rise, that the horizon rises with those, with the object, the plane or whatever that's going up in the sky.
No, but it doesn't. It doesn't though. Like there are multiple videos out there of drones going up straight up into the air, showing that it does not rise or whatever the fuck. Like it just simply doesn't do that. Also, I would love to know how your explanation
I've
for
seen videos that show it rise. So
huh?
And I've seen videos that do show it rise. So.
Okay, well, I'm gonna have to call bullshit on whatever videos you found on YouTube because that's not actually how it works. Second thing is with the Burj thing. I want to know how that differs from a globe Earth. Like, do you think that on a globe Earth, like you don't change your perspective when you go up higher? Like you don't change the perspective from which you view something at. Like you don't see farther on a globe Earth.
I guess you could, but then in my opinion, that's a wash for both. It would work on both models.
Here's why it's not a wash.
Okay.
If you're looking at it from the top of that building on a flat Earth, you should be able to see that sun for a lot longer. It shouldn't set at the same pace that it would when you're down on the ground, but you're still seeing it dip over somewhere. If you're up to the tallest point that you can be on a building on a flat Earth, you should be able to see that sun continuously because you're up there higher with it. It's not dipping down anywhere. Your sun,
you will see it.
Rotates this way, but if you're looking at it from a globe, it's dipping down over the horizon. Why is that?
Well, I mean, if you think about in terms of the differential change in altitude for something that's that far and that high anyways, let's just say 1,000-foot building, right? That's pretty darn tall. 1,000 feet in altitude raise versus the sun, that's how many thousand miles away and how many, say, 1,000 miles up. That's nothing. That's, what is that, a 1% change in altitude, or probably less? I don't know, just off the top of my head. So I don't think that raising, if your question is why would you see it for a lot longer, well, you would see it a little bit longer on a flat Earth too as you go up, but then eventually it will, quote unquote, go over the horizon or drop out of view on a flat Earth too.
Not at the same rate though. That's the thing. And while on your model, the sun would have to change size, and on the globe Earth it doesn't. It stays the same. You can put a solar filter on the camera and watch the sun never change its size as it tracks across the sky. On your model, it should shrink as it gets further away from you.
It depends. I think there needs to be more research done in that area, because I've seen people do videos where they show the difference in perspective of an object on the floor, and just by raising the camera, they can change the size of multiple objects in the field of view of the camera, just by raising the altitude to look like 5-6 feet. So the point is something that far away, something that high and that size, the changing of their size could be minuscule. So I don't know that that's true statement. And I don't know that again, that's an assumption that the flat Earth model says that this angular size of the sun has to change.
No, it would have to. Have to. Sorry, G, but it would have to. If it was moving away from you, it would have to change size. It couldn't stay the same size as it tracked across the sky. That wouldn't make sense. On your model, it would have to get smaller as it moved away from you, but it doesn't. It stays the same.
Well, let's not say words like it has to, because we don't know. None of us know for sure if it would or wouldn't. We're going based on our experience with perspective on the ground with atmospheric refraction going on, etc.
No, it would absolutely have to. If in order for it to work, in order for it to get dark, it would have to get smaller as it moved away from you, because it's not setting over anything. It's just moving away. It's going away from you.
Well, yeah, and it's not just a little bit smaller. We're talking drastically smaller. So, I mean, do you think that the sun like dips below?
Well, what's your evidence for that claim? What's your evidence for that claim?
That it would be drastically smaller?
Yeah.
I'll show you.
Because that's how perspective works.
That's how perspective.
That's how, when you say angular size. Hold on. When you say that the angular size gets too small for that boat to be seen, then you have to understand that that's what it means for the sun when it's going away from you. It's getting smaller, and then you can't see it anymore.
In that example, at that altitude, in those conditions, with that small boat, that 10-foot boat, that's what happens. I'm saying I don't know for sure if that's what should happen with an object like the sun that's so far away, so high in the sky, and so big.
How far?
Here's the Earth right here, and here's the sun on a globe Earth, right? Just imagine that all of these are the same size, right? As it tracks across, and let's say you're here, as it tracks across the Earth, it rises up over this peak when it comes up, and it sets down over here, right? These don't change. The size doesn't change because it's moving across. It's not getting away further away from it.
So the way you drew it is the way that you would see it on a flat Earth, because at the point where it's coming over the horizon.
Yeah,
right. Let me say something real quick before you change that. Keep that up. So at the point where the sun is coming up over the horizon is the same point that you have drawn there. So from this angle of the sun to 12 o'clock, so let's say it's 6 a.m. to 12 noon to 9 to 12 p.m. or whatever, that works. The vantage point of the viewer where they are, it's the same thing as what you've drawn, horizon to horizon.
Okay. Let me show you why it would work on flat Earth.
Why do we see it go below the horizon? Like, I get, like, are you saying that it goes below the horizon because of angular size?
No. It's
okay.
My understanding, the research I've seen, it's due to refraction.
Oh, so you're the whole personal dome theory kind of guy.
Right here. Here's the sun.
Well, again, I don't really know what that means.
Here's the sun. Here's the flat Earth. Here's it. This is the path that it takes, right? If you're here, this is where the sun spins across the flat Earth, right? If you're standing right here, as the sun moves and arches back here, it's going to get smaller as it gets away from you. That's how it has to get dark. Otherwise, how do you explain where it gets dark from?
Well, see, in that, the way you've drawn it,
on the other side.
That's a really good drawing, by the way. The way that you've drawn it, I mean, obviously, it's not to scale, it's not to perspective. If you're at a point on that map that you've drawn, you're going to look at the same horizon to horizon line as you would on a round Earth. The point of that the sun goes down and crosses the horizon is the same point on a flat or round Earth. There's really no difference. It's pulling it down due to refraction.
On a globe Earth, it's going to go curve like back from us and set from us like this, right? On a flat Earth, it's moving like this on top of us. It's not coming across. It's moving on top and pulling away like this. It's getting closer to us.
But by the time it goes, quote unquote, over the horizon, it's the same point as it would be on a flat Earth. I mean, around Earth.
This is the producer.
No. What we're asking is, why is it going below the horizon in the first place on a flat Earth?
And why isn't it some giant angular change in size? There would be a 400% angular difference in size between noon and sunrise and sunset, because that's
where do you get that number?
Basic geometry.
Basic geometry of The $3,000. Well, I don't have it to send to you.
I mean, you were just arguing for angular size earlier, and now you're trying to say, prove to me shit gets smaller as it gets farther away.
Thing is, like, if it stayed the same
in your model, it's getting farther away.
Sun stayed the same size.
It's not.
As it moved across a flat Earth. How would that work? How would it stay the same size when it's up over my head and it moves to Australia? How would it stay the same size? It would have to get smaller.
No, by the time it's gone, it hasn't traveled far enough to make any difference. It's like on a round Earth. Why would the change in distance why would it be the same on all points?
Because it's going around a curve. It's going around a curve.
So as it's going away from you around, is it not further from you than when it is?
Hold on, Chris, hold on. So the explanation for that is that the sun is 93 million miles away, and it's really freaking big. So the change in angular size is not really all that detectable from here on Earth. Now, as we rotate away from the sun, do we get farther away? Sure. I guess technically we do, but it's not enough for us to detect like a change in angular size from our place here on Earth. Whew. That was a really good portion of this particular discussion. I like the multiple different topics that we covered, and I'm glad that Kyle was there to sort of steer the conversation. What I want to know from you is, do you think that Chris here was being very hypocritical in his reasoning for the whole perspective argument or refraction argument or angular size argument for the sun? I would love to hear your thoughts on that. Make sure you leave those comments down below. And hey, while you're down there, be sure to smash that like button and subscribe if you like these kinds of discussions. Don't forget to stand up and use your voice, and I will see you heathens later.